Okay, the last segment of this unit is on Newton's third law of motion and momentum. And just as a reminder, you have some homework problems that will be due with the weight and mass as well as the Newton's second law. All right, so I gave you that worksheet, so hopefully you will be able to work on that. Okay, so we've got a hammer. We have forces created when the hammer strikes the nail. So if you think about it, the one that you really think of is the hammer, the force that the hammer exerts on the nail. But there's also a force that the nail exerts up on the hammer, if you think about it. If you ever swung a hammer and hit a nail and it kind of bounces, well, that's because of the force the nail actually exerts backwards on the hammer. So Newton's third law of motion and momentum is all about what we call action and reaction forces. And basically what Newton's third law states is that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first one. Okay? Oftentimes you'll hear this stated as for every action there is an equal and opposite reaction. Okay, so that's why we call this action and reaction forces. So with a system where I've got two things interacting using force, one of the forces is called the action force and the other force is called the reaction force. It really doesn't matter which one is called which name. It's just important to understand that these two forces are partners in this interaction and they can't exist without each other. The action force and the reaction force are equal in strength and opposite in direction. And like I said, Newton's third law often states for every action there is an equal and opposite reaction. So keeping these ideas in mind, let's try to identify some action and reaction forces because that's really what Newton's third law is all about. Can you identify these action and reaction forces? All right, so if we look at a swimmer moving through the water, just kind of get that picture in your mind. What are those action and reaction forces? Okay, and I have some choices for you. The answer is actually 3. The action force is the force that the swimmer exerts on the water. So the swimmer is actually exerting a force on the water, and the reaction force comes from the water exerting a force on the swimmer. Now, if you think about it, before when we talked about balance forces were equal in strength and opposite in direction. And that's what's happening here with action and reaction forces. So you would think that with these action and reaction forces that nothing would be happening with the swimmer. Okay, sorry about that. Someone came in my room and then an announcement started, so I had to pause it. All right, so what I was saying is if these forces are equal in strength and opposite in direction, why is the swimmer able to move through the water? Okay, well, and that's basically why don't they cancel each other out like they would with a balanced force? Okay, and it's because they act on different objects. So the swimmer is acting on the water and the water is acting on the swimmer, but because they're on different objects, it doesn't always cancel each other out. Other examples of action and reaction forces would be things like walking on the floor. Our feet, when we walk, actually exert a force on the floor, and the floor exerts a force on our feet. The car driving down the road, the tires exert a force on the road, and the road exerts a force on our tires. And rowing, like on the water, the oars exert a force on the water, and the water exerts a force on the boat that actually helps push it through the water. So these give you some ways to identify these action and reaction forces, but sometimes it's not as obvious to do. Okay, for example, if we have a falling boulder, let's try to identify those action and reaction forces. Well, it's obvious that one of the forces, and we'll call it the action force, is Earth's gravitational force, because we know that's what's pulling the boulder down as it's falling. But the reaction force is actually a little harder to identify, because it's like, okay, what other force could be there? But what you have to remember is that the Earth is exerting a force on the boulder and it's equal and opposite. So at the opposite side is the boulder is exerting a force on the earth. So the reaction force is the boulder's force on the earth. So if you think about it, in some ways the earth is actually falling up to the boulder instead of the other way around. It's actually a little bit of both. Well, if that's what's happening, if the earth is actually falling up, why don't we feel the earth move when things fall? And that has to do with the difference in mass. If you compare the mass of the earth versus the mass of the boulder, it's a very small, teeny tiny acceleration. The same sort of thing happens every time we jump or we step off a curb. The earth actually accelerates just a little bit up to meet us. But we don't feel that because the difference in mass, the earth is so massive and compared to us. So the force that we exert does not cause that big mass to accelerate very much at all. It's kind of like with a cannon and a cannonball. Okay, the action force is the cannon on the cannonball, and then the reaction force is the cannonball on the cannon, which actually causes the cannon to kick. So if you think of it this way, with the forces are equal, okay, that's why they're equal in size. The cannonball comparatively has a small mass, whereas the cannon has the large mass. But if you look at their accelerations, the cannonball has the larger acceleration and the cannon has the smaller acceleration, even though the forces are equal. And this leads to the kind of the math part of Newton's third law, which has to do with momentum. Momentum is the product of an object's mass and its velocity. Now remember, any object at rest has a momentum of 0 because it's not moving. So the momentum formula is mass times velocity. And most of the times the unit is kilograms times meters divided by seconds. It just depends on the problem that you're given. So this leads us to the law of conservation of momentum. Basically says that if there's no net force acting on the system, then the total momentum does not change. So as long as we don't get a new force introduced, momentum will always stay the same. So in a closed system where I have two objects interacting, if I lose momentum from one object, I have to gain that momentum in another object. So momentum can be conserved from one object to another. So if a group of objects exerts forces only on each other, then their total momentum does not change. And you can see that on the examples here with the train cars. We've got 3 different collisions. In this one, before collision, okay, we've got one 300,000 momentum, kilogram dot meters over seconds. Okay, it's moving at 10 meters per second, and the momentum of this car moving at 5 meters per second is 150. They collide and the cars bounce off each other. Notice that the numbers stay the same, 150 and 300. Okay, so momentum before is 450,000, momentum after is 450,000. When one car moves, now this is kind of like what happens with pool balls, okay? One comes in, hits it, the other one starts moving, the one stops, okay? If you look here, momentum before is 300,000, and then after it is 300,000, okay? When I have one car moving in the cars couple, okay, 300,000 units of momentum, okay, and it's moving at 10 meters per second. Now the combined two of them only move at 5 meters per second, but the total momentum is still the same. It is what we call conserved. So we have a momentum problem here. A 0.25 kilogram ball was dropped from a bridge. The graph shows the momentum of the ball from the time it was dropped until it hit the river below. Okay, at what time did the ball have a momentum of 0? Okay, so the time that it's 0 is right here. So what is it doing at this point? Okay, it hasn't even been released yet. Okay, so t equals 0 seconds. Okay, and the ball has 0 momentum before it is released. Question 2. At what time did the ball have the greatest momentum, and what was the peak momentum value? Well, its highest momentum is here at 2.5 seconds, And the peak momentum value is 6.5 kilograms dot meters per second. Okay, what is the ball's speed after 1.25 seconds? Okay, hint to use the graph and the momentum formula. Okay, so 1.25 seconds is this line right here, and we go up, okay, and its momentum is about halfway, so 3.25 kilograms dot meters per second. Oops, sorry. There we go. All right, so let's write that up here. Now we represent momentum using the letter P. Okay, so P equals M times V. Okay, our P we said was 3.25 kilogram meter divided by second. It looks kind of weird. Okay. The mass of the ball, okay, we had from the first problem, and that was 0.25 kilograms. And our V is what we're looking for. Okay? So what we do is we take 3.25, and that is equal to 0.25 times our V. If I divide both sides by 0.25, then I get 13. And because V is a velocity, it is meters per second, and that is my V. Okay? So that's how we solve those things, and they're pretty easy. All right, and this basically just takes us through there. Answers to 2 and our answers to 3, which we just wrote out a little bit more detailed. Okay, now in your handout packet, I want you to highlight 12.3, and you have one little vocabulary word, and that is it. Now the other thing you will have to make up when you get back, as long as we end up doing it, this is the plan. We will have a lab that you can actually very easily do by yourself. That's not a problem. And I'm sure that I might have a couple of other people who will have missed it. So if you want to try to work together with them. And then on Friday is our test. So make sure that you're working on your study guide. And be prepared to take your test pretty soon when you get back, so that way then you can stay caught up and keep caught up with everybody. Okay? Hope you have a great trip.